Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, we're back again to continue this discussion of Hamaker constants and surface energies. Just a brief review. Lecture 1 of week 2 was concerned with the definition of something called the Hamaker constant that describes how macroscopic bodies interact one with respect to another using these van der Waals interactions. The second lecture in week 2 was a brief introduction to the concept of surface energies gamma. And in this particular lecture, we're going to use something called the Derjaguin approximation to connect surface energies to Hamaker constants. And we'll show you how these surface energies can be estimated by measuring the force of adhesion between a spherical tip and a flat substrate. So that's the end result of this lecture will be that the derivation of that fundamental result. So again, what we have here is we have a solid. Solid is comprised of atoms. The separation between two rows of atoms is a parameter that we're going to refer to as A0. And what we want to do is we want to think about the situation of putting wedges in between the atoms and trying to separate the material, the bulk material, to form two surfaces. When we do that, we require a certain amount of work, and that certain amount of work is tied up in the surface energies of the two new surfaces that were created. So here what we show is the solid now has been split into two. The separation between the two surfaces of the solid are a few times this interatomic spacing parameter A0. And the question now becomes, if these two surfaces interact, one with respect to the other, strictly by a van der Waals force, what is the net energy of attraction that these two surfaces would have when we're considering planar surfaces now? So before we considered the case of a sphere interacting with a flat plane, in this lecture we're more focused on two flat planes interacting one with respect to another. So the way to solve this problem is to go back to the fundamentals. Just briefly recall the molecule plane interaction that we discussed back in lecture 1. The idea is simple. We've got a molecule or an atom that's positioned a certain distance d away from an infinitely large flat plane. And we're going to consider how that molecule interacts with all the molecules in the slab of material. The way that calculation is performed, you have to basically integrate the interaction, the van der Waals interaction between the atom exterior to the bulk material with all the atoms inside the bulk material. And when you do that, you end up with an expression that's given in the last equation here. This is just a restatement of something we've already seen in lecture 1. We're going to extend that result now to calculate the interaction potential energy due to van der Waals interactions alone between two flat planes that are now separated by a distance d. And in order to get an answer for this interaction potential energy, what we do is we consider all the atoms or molecules in a slab of thickness d zeta. That slab is located a distance d plus zeta from an infinitely large flat plane. The area exposed to the large flat plane, that area is referred to as A. And in this particular calculation, that parameter A is going to be used to normalize the interaction potential energy. So we're going to calculate the interaction potential energy between two planes divided by that surface area A. And that the result is derived by using the result from the previous transparency, previous slide. You just basically have to integrate that result over the entire slab. And the arithmetic in this case is pretty simple. The end result is the last equation here. This plane-plane interaction energy normalized by the surface area A is just equal to the Hamaker constant H divided by some numbers, 12 pi, and the interaction potential energy in this case goes as 1 over d squared, 1 over the separation between the two planes. So this is another fundamental result that comes from incorporating this van der Waals interaction energy and integrating it over all atoms in order to understand how two macroscopic solids might interact, one with respect to another. It's probably worthwhile to estimate typical values for these Hamaker constants. We've introduced this constant H on a number of occasions, but we actually have not estimated how big it is. So in this particular slide, I just go to the textbooks. I find that typical values for the Hamaker constant C are on the order of 10 to the minus 77 joules meters to the sixth. Typical number density for atoms in solids is a number on the order of 3 times 10 to the 28th cubic meters per cubic meter. So that's the number of atoms per cubic meter that typically is appropriate for solids that you come into contact with. And what you find is that typical value for this Hamaker constant's a number on the order of 10 to the minus 19 joules. So if you look, for instance, there's a very, very nice review article by Boot, Capella, and Kappel, right? They list Hamaker constants for a large variety of materials. What you'll find by looking at that list is that typically most solids have values between 0.4 and 4 times 10 to the minus 19 joules. So that sort of sets the energy scale for the interaction potential energy between macroscopic solids that we're actually discussing. It's always useful to step back and do a simple confidence building example and ask for instance, how strong are these van der Waals surface forces? We've calculated the interaction potential energy for two planes separated by a distance d apart. The result of that calculation is shown in the first equation on the left. The plane-plane interaction potential energy divided by the area A that's appropriate is just minus h over 12 pi d squared, where d is the separation between the two planes. And h is a number on the order of 10 to the minus 19 joules. So we can ask a real simple question. If we have a rod indicated by that solid red cartoon, right, and we have that extending down, and we push it up next to a mass next to an object which has a mass m, we can ask how big is the cross-sectional area that supporting rod required in order to hold the mass m up, right? So that you can actually lift the mass m strictly based on the interaction between the two surfaces that form right at the intersection between the rod and the mass m. So the answer to that question depends on what the van der Waals force is across the two surfaces that are separated by this distance d. You can get that force by taking the negative first derivative of the interaction potential energy. That's sketched out here. And in particular, when d, the separation, is equal to A0, the lattice constant between the two, between atoms in the two solids, then you can estimate the magnitude of the force and compare that to, let's say, the gravitational force that's pulling down on this mass m. So the gravitational force is just m times g. The van der Waals interaction force is indicated by the formula on the left-hand side of the equal sign. And in this way, you can estimate, for instance, what radius of a rod you would need in order to lift up a mass m just due to van der Waals forces alone. I go through an estimate of that mass depending on the radius of the supporting rod. And I actually plot it versus the diameter of the supporting rod. And the answer is quite surprising, right? For instance, if you have a rod that's got a diameter of 0.02 meters, that's 2 centimeters. Well, 2 centimeters is about that big, right? This simple calculation says you should be able to hold up or lift up about roughly 8,000 kilograms of mass, just based on van der Waals interactions between the atoms on either side of the interface that's formed between the supporting rod and the mass m. Well, 8,000 kilograms, that's the mass of a fairly heavy-duty truck, and it just basically is telling you that two solids pressed one against the other should adhere very strongly. Of course, experimentally, this doesn't happen, right? You can take a rod of 2 centimeter diameter, you can push it onto a truck, and you can try to lift the truck up, and there will be no adhesion, very, very small adhesion. You will never get anything close to the ability to lift 8,000 kilograms. And the question is why? And the answer, of course, is that it's very hard to get two surfaces in which all the atoms are spaced an atomic distance a0 one from another. If you could achieve that condition, then this calculation would be relevant. But the surfaces tend to be rough. There tend to be oxides that form on these surfaces, contamination layers. So you never achieve this very strong van der Waals binding force if you just push one material onto another. But nonetheless, it's a very illustrative, very useful example because it does show you that these van der Waals forces can be quite strong. And that's the reason I included it in this discussion. The other point to make is that you can estimate the surface energies, these parameters gamma that we discussed in the previous lecture. You can relate those directly to the Hamaker constant H, and I illustrate that connection in this particular slide where I connect the interaction potential energy per unit area times the amount of work required to produce an area dA, and that amount of work dW divided by dA, that's referred to as twice the surface energy gamma 1 of the surface of the material that's used in this particular example, right? And so just by very simple algebra, you can see how the surface energy parameter is related to the Hamaker constant. It's a bunch of geometrical constants, 24 times pi, divided by the radius, or divided by the atom-atom separation squared between atoms in the solid that's under consideration. So these Hamaker constants and these surface energies are very closely related to one another, and I hope that's clear from this discussion. I'd also like to emphasize this Derjaguin approximation, which allows you to connect adhesive forces that are measured experimentally with these plane-plane interaction potential energies that we can calculate theoretically. And the case for this connection is made in this slide. The algebra is reasonably straightforward. At the end of the day, you find that there's a force of adhesion between a plane and a sphere. This is indicated in the last equation on this slide. That adhesive force, which is something that you can experimentally measure with an atomic force microscope, that's related to this very fundamental quantity of the interaction potential energy between two planes separated by a distance d, right? By just a simple geometrical factor, which is 2 pi times the radius of the tip, or the radius of the sphere that's separated from the plane by a distance d. So this just simply means that these interaction potential energies, which are what theorists tend to calculate, they can be verified experimentally. They can be measured experimentally if you can do a very careful measurement of the adhesive force between a plane and a sphere. And if you can in particular measure the force of attraction of a sphere as it comes closer to a flat plane, right, as a function of the separation distance d, if you know the radius of the tip or radius of the sphere, it should allow you to estimate material properties, surface energies or interfacial surface energies, depending on whether the sphere and the substrate are made of the same material or if they're made of dissimilar materials. So this is a very fundamental result. It's very interesting, and it technically only applies if the interaction force between the sphere and the plane is due to these van der Waals forces, right? If you've got electrostatics or magnetostatics involved, this approximation will definitely break down. But in the limit where the interaction is only due to van der Waals forces, this is what the theoretical results would predict. The Derjaguin approximation is a little bit more general than what I just indicated on the previous slide. In particular, it emphasizes the force between two objects of arbitrary shape can be calculated in terms of the force that acts between two planes separated by a distance x. So if you want to know the force between two objects, one object could be of arbitrary shape, the other object could be a flat plane, for instance. That's f of d, that's the result on the left. It's just related to the interaction force between two planes, f of x, multiplied by how the area of the objects vary as a function of x integrated over all x. You can actually calculate the interaction force in a very straightforward way. I just worked through an example to illustrate this case, just to show you why it might be useful and give you a sense of how it could be used. So in this case, I've got a cone of half angle alpha. I've got that position, the distance d, above a flat plane. I have to calculate the area of a small slab, and I have to calculate that area as a function of x, the separation of that slab from the flat plane. Once I know that the area is a function of x, I can take its derivative. I can use the Derjaguin approximation as I indicate. You have to sit down and work through the algebra yourself to understand it. But at the end of the day, you then have an expression for the interaction force as a function of d. In this case, it's of a conical tip with a flat plane. So this is just an example of Derjaguin approximation that might be useful as you work your way through different situations in atomic force microscope experiments that you might be interested in performing. So the implications of this Derjaguin's approximation, they're quite far-reaching. Basically, the end result is that the force of adhesion between, let's say, two spheres, spheres of radius R1 and R2, can be related back to this very fundamental quantity of the interaction potential energy per unit area. In the case that one of the spheres has an infinite radius, that's equivalent to a flat plane, so that if you let one of the radii, R2, for instance, equal to infinity in this equation, then you reduce back to the results of a sphere radius R1 interacting with a flat plane. And this approximation is very useful because it allows you to convert these forces of adhesion back into surface energies. And if you can convert them back into surface energies, then you can also relate them to Hamaker constants, which in principle is a useful thing to do. So That's the point of this particular lecture. It's trying to emphasize this connection between these quantities that are discussed theoretically and how you might be able to measure them experimentally. So thanks for coming, and we'll continue on with this discussion with the fourth lecture in week 2. That'll be coming up next.